Okay. So thank you, Rajaram, and I think today is the means the second day and last day of this FDP, and I means congratulate you for organizing this FDP, and particularly for this IS 1893 Seismic Code, which has published recently. Many changes has been done, and in addition to structural design and soil characterization, and particularly liquefaction potential also. So I will be discussing this evaluation of liquefaction potential, particularly how to find the liquefaction susceptibility of the soil before designing any structure on that particular site. So, and means revised version, the procedure mentioned in IS 1893 Part 1, 2025, and the major means revision as compared to 2016, that I will highlight. What is the best means difference in it was there in 16 and now 25, particularly liquefaction potential. So before discussing the codal provision part, I will first cover the introduction, means the basics of liquefaction and why it is important, and why liquefaction study is carried out nowadays, for all important critical structures, which was not there in our previous code, like 2002 version. Liquefaction potential evaluation was not there, and in 16 it was included as a appendix, and now in 2025 it has been included in the general provision guideline part, that is part 1. So these are the outline. First, I will discuss the fundamentals of liquefaction and what are the consequences of liquefaction, factors affecting liquefaction, and the simplified procedure for evaluation of liquefaction potential, whatever mentioned in our IS 1893 Part 1 2025 code. So for soil, as you know, for soil, shear strength is the most important parameters. So, and the soil fails in shear, so we need to consider the shear strength of the soil while designing the structure in it. And liquefaction particularly occurs when loose saturated silty sand, or sandy soil subjected to earthquake loading, maybe cyclic or dynamic load. In that case, what happened? The normal stress is transferred from soil matrix to pore pressure due to the tendency of volume contraction of loose soil in an undrained condition, which results in the reduction of effective stress and partial or complete loss of strength and stiffness of the soil. And basically it occurs in uniform fine grained loose round shaped soil deposit of recent origin. And the concept of liquefaction particularly has been introduced by author Casagrande in 1936, and serious attention have been taken because of this failure after this Alaska, Niigata, Kobe, Vuj, and our recent Nepal earthquakes. If you see this definition of liquefaction, in this definition itself you can find what are the major factors affecting it. So for a soil to liquefy, first condition is it has to be the soil state of the soil should be in loose or medium dense state, and the type of soil should be silty sand or sandy soil. Why? Because we are now treating soil will behave like a fluid. So shear strength of the soil is tau is C plus sigma tan phi. So it shear strength is function of two strength parameter, that is cohesion and angle of friction. So if it is a clay soil, there will be always cohesion factor. So that's why in sandy soil only your shear strength will be sigma dash tan phi, which is function of only friction angle and the effective stress. In that case, there may be chances of pore water pressure increase, and when it matches with the total stress, the effective stress becomes zero. So when there will be chance of increase in pore pressure? So the condition is if you have undrained boundary like hard stratum at your means soil site, if you have means hard stratum or rocky strata are the means below, then there is less drainage path. So under that condition, if certain shaking or any vibration or dynamic loading is there, then under this ground vibration there will be chance of increasing water pressure. So your total stress is always remains constant, that is gamma into z. So once your pore pressure is increasing, once it matches the total stress, your effective stress term becomes zero or negligible. That case your shear strength will be zero. So the condition and the soil will behave like a fluid. So means we need to check the type of soil, whether it is sandy type or cohesive type, clay type, and the state of the soil. Means loose, dense, medium dense. So under loose case, there may be chance of more void space. So if there is a space, void space, then the pore water pressure means built up will be more, and it may match the total stress. So these conditions we need to check. And even based on our basic geotechnical characterization report, we can see what is the existing field condition. Depending on the density gradation, means our sieve analysis result, this can be classified: type of soil, density of the soil, and whether it is saturated or not. So under dry condition, if soil deposit is completely dry, no chance of liquefaction is there. Only under saturation condition, there may be chance of pore water pressure to build up. So if no water pressure means is there, then there is no chance of means effective stress becoming zero. So that's why these are here in this definition itself, all the factors has been mentioned. I will discuss one by one in detail. You can see there are a few damages due to this soil liquefaction. Here, this is due to 1964 Niigata earthquake. The building, these structures has been toppled due to the lack of bearing support here. The soil failed, like the soil behaved like fluid. So that's why the structure means collapsed. So there is the design of the structure was perfectly fine, but due to lack of bearing support, the structure toppled. This is the means liquefaction image of a during the Loma Prieta earthquake, and this image is port structure failure in Kobe earthquake, and this last one is 2001 Bhuj earthquake soil liquefaction image. Theory, whatever I had just discussed. So for sandy soil, there is no cohesion. So your shear strength is depends on your effective stress and friction angle, sigma n dash tan phi. And when this sigma n becomes zero, so your shear strength will be zero, and soil will behave like fluid. So effective stress is total stress minus pore pressure. When this pore pressure increases under dynamic or earthquake loading condition, when it matches the total stress, then there will be complete loss of strength and stiffness of the soil. That case, the gradient is hydraulic gradient is treated as critical gradient. And the basic mechanism of liquefaction is the loss of strength occur due to transfer of intergranular stress from grain to pore water. So if you see that this first image, this shows the means at rest condition where there is no shaking, and this shows the contact forces, particle to particle contact, and this blue color shows the static pore pressure. And during shaking, the means under undrained condition, pore water pressure increases, and this particle to particle contact reduces. Means there is loss of particle to particle contact, or you can say grain to grain contact. If this transfer is complete, then there will be complete loss of strength. Soil will behave like fluid, and if it is partial, then there will be some partial loss and some residual strength you can get. So at rest condition, soil state, soil grains, and pore pressure. This is the contact pressure, and this is means after the shaking. Here I will show you one image. In this video you can see even tall building is there, and here if you see the soil deposit at shallow depth, there is a loose granular sediment, and under loading and earthquake shaking, Actually, this is the image, a real image of structure means which was fell during San Francisco earthquake. So here the structure, tall building was designed perfectly fine, but there was a means sediment layer at the shallow depth. If you see here, here at shallow depth means there is a loose granular sediment, and it was means under saturation condition, means groundwater table was at shallow depth, and under earthquake loading what happened, this was saturated, and under shaking this the pore pressure increases, and this particularly at shallow depth, this loose sediment layer, it filled, means like it loses its shear strength, and this soil behave like fluid, and because of this failure of this thin layer only, the means bearing contact between the foundation and the structure, that is the loss of bearing support, and the failure of the structure happened. So this means particularly this happened, structure collapsed due to this increase in pore water pressure and loss of this particle to particle contact and this loose sediment means layer which was present at shallow depth. If this layer was means present at greater depth, it may not reach the foundation of this structure. So that's why if suppose you have a liquefiable layer below 20-25 meter, that layer may not affect your foundation. But if this liquefiable layer is at shallow depth, means there may be a risk or chance of failure of the structure. We need to be careful while designing the structure. So consequences of liquefaction, there will be loss of bearing support and settlement. Mostly you will have a non-uniform settlement, very rare case uniform settlement, because earthquake load is random loading, so uniform settlement is very rare. Flotation of buried structures such as underground tanks, and lateral support, loss of lateral support, increase in lateral pressure against retaining walls. If the means like focus is close to the retaining structures, then lateral spreading and lateral flow. Difference between lateral spread and lateral flow is, if you have limited deformation, then that is lateral spreading, and if you have excessive means settlement, or you can say deformation in horizontal direction, that is called as lateral flow. I will show you few images of means this failure. This shows the image of a bearing failure, which the, one of the consequences of soil liquefaction. And Niigata 1964 Niigata earthquake. Here you can see there is complete loss of means bearing support. The structure is perfectly fine, but the soil under soil liquefaction, when the soil behave like fluid, there was means complete loss of bearing support, and this is the typical example of bearing failure. And this shows the lateral spreading means consequences of lateral spreading. Also 1964 Niigata earthquake example. Here you can see how the pore structure has been spread laterally. This shows the ground failure due to soil liquefaction, not 1994 Northridge earthquake. And here you can see the failure of the slope, particularly due to the soil liquefaction. When the soil behave like fluid, means liquefied, then this type of failure occur. And this is the image of a lateral spreading 1995 Kobe earthquake in Japan. So here you can see the gap, how much the ground has been spread laterally. So you can imagine after the, and this is due to the soil liquefaction only, not due to any additional cause. And the right side is also a lateral spreading image. Here you can see the gap of and this ground. This is another example of differential settlement of 1919 and Chichi earthquake. And here you can see that there is a huge difference in the roll level. Here, this was the initial position, and this much differential settlement had occurred due to the soil liquefaction below this bridge apartment fill. And this is typical image of Bhuj earthquake, 2001 Bhuj earthquake. And this is the recent our 2025 in 2015 Nepal earthquake, soil liquefaction. And here you can see liquefaction induced lateral spreading, the field image which was taken after the Nepal earthquake. Then coming to the factors affecting liquefaction, as I mentioned the first slide itself, while defining the liquefaction and what is liquefaction, there everything is mentioned. Like first condition is type of soil. We need to see what is the type of the soil, whether it is sand or clay. So mostly sandy soil is prone to liquefaction, and clay soil not non-liquefable. Why? Because for clay you will always have cohesion term, so your shear strength will not becomes zero. So if suppose effective stress is zero, then also you will have tau is equal to c plus sigma tan phi. So your sigma tan phi becomes zero, but c will always be there. Then that's why the strength of the soil will not be zero in case of clay soil. So type of soil means if it is sandy soil, then only there is a chance of liquefaction. First, we need to check the condition of the soil. Characteristics of the soil particles, like gradation, shape, size of the particle, so which we can get from our sieve analysis result, like what type of soil and group, like well graded, poorly graded, gap graded. So if the soil is well graded, that means different particles are present, so particle to particle contact will be more in well graded shape. But in case of poorly graded shape, then there most of the particles are rounded shape or of uniform shape, uniformly graded shape, means soil we can say. So that case, there will be less particle to particle contact. If less particle to particle contact, then with the rise in pore pressure, there will be loss of grain to grain contact. So gradation means poorly graded soil or uniformly graded soil are more prone to liquefaction. Shape, when it comes to shape, rounded shapes are more prone to liquefaction as compared to angular, because angular shape or irregular shape you will have more particle to particle contact. However, rounded shape less particle to particle contact. Next is your drainage condition. So under undrained condition only, there may be chance of pore water pressure to build up. If you have a drain boundary, then under means dynamic load or shaking, there will be means dissipation of pore pressure, not built up. So this condition is also important. Your drainage boundary, whether you have a presence of hard stratum or means like drainage material. So undrained condition, more chance of liquefaction. Confining pressure. Next is confining pressure. Confining pressure means at shallow depth you have less confining pressure. If you go greater depth, there will be more confining pressure. So more confining pressure means more resistance you are getting. So more resistance means less chance of liquefaction. So particularly means low confining pressure, high chance of liquefaction, means that is at shallow depth, more chance of liquefaction. That's why if your soil is liquefying means below 20 meter, your structure may not fail. So means because that below 20-meter soil, liquefiable soil, it may not reach the your foundation level. Next one is your relative density. So loose or dense, loose soil, more chance of liquefaction because there is more void space. So pore water pressure can increase at faster rate, and it may match the total stress. Dense case, less void space. Even pore water pressure is building up, it may not match the total stress. So your effective stress means will not be zero in case of dense condition. Then magnitude and duration of loading, higher magnitude and longer duration of shaking, more chance of liquefaction. Then coming to liquefaction potential evaluation, there are means different methods are available based on lab study, field study, and numerical simulation. So based on the availability of facility, we can go for the appropriate methods. However, in our ICE code, field study method is recommended because in the field means study case, what happened, you can simulate the real field scenario, whatever the soil condition and the exact confining pressure, density of the soil, in situ density, and also the means variation of your soil type, that can be simulated in case of field study. However, lab study, we can do the representative sample. We need to collect the sample and try to create the similar environment in the lab, which may not reflect the exact field situation. That's why field studies recommended for liquefaction potential evaluation in our IS code. And means depending on the facility, lab study, there are different facilities, like you can use vibration table and cyclic triaxial test, simple shear and geotechnical centrifuge for means creating the liquefaction, like vibration, and the soil sample you can see the like examine the liquefaction behavior. So this is the vibration table available at IIT Roorkee. So here you can, in this tank, you can fill the liquefiable soil and apply horizontal shaking and see the means behavior of the soil, how the pore pressure is building up, and the soil, how the soil is behaving under like horizontal shaking condition. Cyclic axle test, what this is available in IIT Roorkee and most of the IIT. This cyclic axle test is, I think, all have now. Even we are also having say this setup in our IIT. So here small means cylindrical specimen we can prepare, and here we can try to simulate the existing field confining pressure we can apply. And here we can apply the shaking like cyclic load in by means of the actuator, and like sinusoidal loading we can apply uniform sinusoidal loading. Under this condition we can see whether this soil sample is filling or pore pressure is matching the total stress or not, and means the liquefaction potential can be examined. This is the triaxial system available at IIT Kanpur. I was used this setup during my PhD, and this is the setup we have developed here in IIT BHU. And then coming to the in situ geotechnical test, the basic geotechnical test means recommended for in type of project are like SPT, standard penetration test, cone penetration test, dilatometer test, pressure meter test, and vein shear test, like SPT, CPT, DMT, PMT, and VST. So out of these, this SPT, CPT, DMT, and another one is shear of velocity based test, means the liquefaction potential evaluation is mentioned in our IS code. I will discuss in detail. So if you see this in situ geotechnical test, the basic difference among these five tests are, for SPT test, you need a pre-borehole. First, you need to dig the borehole. Then you can drive this means your sampler. It is attached to the drill rod and this hammer. So here we are applying the impact load, and under this impact load we are trying to calculate the resistance of the soil in terms of SPTN, like for 30 centimeter of penetration of this sampler, how many times we have dropped it, number of blows for that particular 30 centimeter of penetration. So by applying impact load in terms of this hammer blows, we are relating the resistance of the soil. Higher the number of blows for that particular penetration depth, it represents the stronger the strata. Less number of blows represents weak strata. So CPT, if you compare SPT and CPT there is no need of borehole. Directly you can drive the cone pentometer and you can measure the tip resistance and friction resistance. So that way this boring or borehole cost can be saved in CPT case. And here we can get the continuous profile, because CPT, the rate of penetration, it is up to you, you can fix it, means the rate of penetration of the cone pentometer. However, SPT, there is a provision that at least you should have the borehole depth 1.5 meter. Every 1.5 meter you need to take the SPT envelope, like this number of blows for 30 centimeter of penetration. Particularly 45 centimeter, first 15 centimeter you need to discard, and then 30 next to increment you need to take the number of blows. So, and DMT also, there is no need of borehole. Pressure meter, borehole is needed, so you need to dig the borehole, then you need to drive the pressure meter probe, and pressure volume relation you need to build up, and based on that pressure to particular expansion of this pressure meter probe, we need to relate the resistance. And vein shear, there is a need of pre-borehole. You need to first dig the borehole, then drive the Vensier means apparatus and rotate. So here we are applying the torque, and by that means we are calculating the resistance of the soil. So basic difference, this is the basic difference between this in situ test, and depending on the project type, we need to recommend any of the field test for geotechnical investigation. So, and for liquefaction potential, particularly SPT, CPT, DMT, and VS is recommended. And the procedure based on this SPT, CPT, DMT, and VS is mentioned in our IS 1893, Part 1, 2025. So, for this liquefaction potential evaluation, first we need to see what is means this liquefaction potential. So, what here we need to find the factor of safety against liquefaction. So, factor of safety FSL means factor of safety against liquefaction. So, this is the capacity to demand. So, here this capacity represents what? What is the means resistance of the soil against liquefaction. Then demand means what is the seismic demand in that particular region. So based on we can say capacity to demand or resistance to driving resisting force to driving force. So this seismic demand, as you know, the our India is divided into different seismic zone. In this 2025, zone 6 has been included. So different region have different seismic demand. So depending on that, the PGA value is different. So demand will be different for different site, and capacity, it depends on the soil capacity, means resistance of the soil. So ratio of these two, capacity to demand, we can say it is the factor safety against liquefaction. If you are getting this factor safety greater than 1, means your resistance is more than the demand, means soil is safe against liquefaction. But there are few guidelines mentioned what to be considered for design of structure. So at least the factor safety against liquefaction should be more than 1.2. Then it is stated as safe against liquefaction. And so coming to seismic demand on the soil, here this shows the screenshot of this means from IS 1893 part 1 2025. If you see, every city it has a zone factor, and this zone factor is nothing but your PGA value. So different city, they have particular seismic zone and zone factor. Here if you see, we have starting from zone 2, 3, 4, 5, and 6 in 2025, and the corresponding PGA for zone 2.15, zone 3.25, zone 4.35, zone 5.5, and for zone 6, particularly this dark maroon color region. So completely this Andaman Nicobar and this northeast northern part of India, this completely, and this portion is also zone 6. So for that region, we need to consider 0.75 G. So 0.75 is a huge amount, but while designing the structure, we need to be careful while considering the factors. If you compare this factor with our previous 2020, 2016, 2016 code, so for zone, there was no zone 6, only zone 2, 3, 4, and 5, and for 2 it was 0.1. Now from 0.1 to 1.15, then earlier 0.16, then 0.24 and 0.36. So maximum PGA value we had considered 0.36. Now for zone 6 we need to consider 0.75. So what it represent, even in this code, for each seismic zone, the expected maximum expected earthquake magnitude also mentioned, like MW value is also mentioned. Zone 2 expected magnitude of earthquake is 6, and zone 3 6.5, and zone 4 7, zone 5 7.5, and zone 6 is very high 8. So this what is represent, this represents a demand. Suppose if you are here in zone 2, so there may be chance of 6 magnitude of occurrence of 6 magnitude earthquake, and not more than that. And the seismic demand, like PGA value, is expected PGA is 0.15 G. Yes, 0.15G. So this represents the seismic demand for different location, like different region. So depending on your project location, you need to pick the particular PGA value and the expected MW magnitude. Yes. Ex- ex- any question? Rajaram, any question?
No questions, madam. You can move forward.
Okay. Okay. So now cyclic stress ratio, like the demand part. So means the basic background of cyclic stress ratio and the principle was discussed in Wood et al. 2001 paper, and then the concept has been taken from that, and similar expression has been given in our 2016 version of our IS code. So CSR is the ratio of cyclic stress to average initial effective vertical stress, which is nothing but your 0.65 a max by g total stress to effective stress ratio into stress reduction coefficient. So the stress reduction coefficient is multiplied because there will be non-linear deformation of the soil during the earthquake loading. So to consider that, this stress reduction coefficient has been included, and this was function of depth. So with depth, this reduction factor will change. So if you see here in this CSR cyclic stress ratio, which is nothing but the demand, it is function of your A max by G, that is the PGA, which in the previous slide we had discussed. For different region we have different PGA value, and this total stress to effective stress ratio, and RD, like stress reduction coefficient. So in this IS 1893 part 1 2025, here also similar expression has been mentioned. So in place of cyclic stress ratio, that is CSR, here it is mentioned stress ratio only, like SR. And the expression is same, 0.65 a max by g, total stress sigma v naught to effective stress, that is sigma v naught dash into RD. So main change in this expression is A max by G is nothing but your PGA value, which you can get from the code for particular city. You have a zone factor that you need to consider here. Total stress means gamma into Z. If you know the soil density and depth, you can calculate the total stress. For effective stress, you need to know the water table information. Once you have the pore water pressure information, so total stress minus pore pressure will give you the effective stress at that particular depth. So the RT here is, earlier the RT was, if you see here, this stress reduction coefficient was only function of Z, that is the depth. However, in our new code, this RT is function of both magnitude of earthquake and depth. So magnitude M is the magnitude of largest likely earthquake, which is mentioned in the code also. If you see here, for every region we have the MW value, that is maximum magnitude of expected earthquake. So this the RD is function of that M and depth. So here RD is e to the power alpha z plus beta z into M. So alpha z beta z are function of this depth and this magnitude of earthquake. This is the means you can say difference in the this 2025 as compared to previous one 16. 2016 only RD was calculated using this expression, function of Z. Here M has been included, magnitude of earthquake. Then so demand is demand cyclic stress ratio or SR stress ratio. You need to have the Amax value and the soil properties and stress reduction coefficient, and in which region you are, what is the expected magnitude of largest likely earthquake. Then coming to the cyclic resistance ratio, which is nothing but the capacity of the particular soil deposit against liquefaction. So this capacity, it is calculated based on the field this geotechnical test results, that is SPT, CPT, and VS and DMT. So So for this CRR, cyclic resistance ratio, first we need to calculate the cyclic resistance ratio for an earthquake of magnitude 7.5, because the procedure mentioned in Wood et al. 2001 was mentioned for MW 7.5, and if you have means different zone like zone 6, where you are expecting earthquake of magnitude 8, so in that case you need to multiply MSF, that is the magnitude scaling correction factor, and K sigma is the high overburden pressure correction factor. So first, the CRR 7.5 we can calculate based on SPT, CPT, VS, and DMT value, and we can multiply MSF, K sigma, depending on the seismic zone, because for different seismic zone different chance of this earthquake and different magnitude, and K sigma, if you have this high overburden pressure zone, then you need to multiply the K sigma. So MSF, if you see here, MSF is function of magnitude of earthquakes. This is the 1 plus MSF max minus 1, 8.64 e to the power minus 0.025 m minus 1.325. If you see here, in addition to magnitude of earthquake, that is the M, it also function of MSF max. So what is MSF max? MSF max is the maximum value of magnitude scaling factor. So if you see here, this maximum value of this magnitude scaling factor is also function of your soil properties, that is the CPT value and the SPTN value. So QC1NCS is the corrected tip resistance, which is obtained from CPT value, CPT test, cone penetration test, and N160CS is the corrected N value obtained from SPT test. So this is the change as compared to your 2020 2016 version and this 2025 version. Previously, if you see, previously we had considered for MSF this expression, that is 10 to the power 2.24 divided by MW to the power 2.56. So it was only function of magnitude of earthquake, not soil properties. And if you see here, so in addition to magnitude of earthquake, the MSF is also function of your soils means strength parameters like the tip resistance and this N value. Then coming to overburden pressure correction factor, K sigma, it is calculated using this expression 1 minus C sigma ln ratio of effective stress to PA is the atmospheric pressure, and this value is limited to 1.1. And here if you see, this C sigma is also function of your corrected tip resistance and corrected SPTN value, applying the fine content correction factor. So depending on the availability of the result, if you have, then you can calculate using this expression. Otherwise, you can calculate this CRR 7.5 from figure 6, that is given for your 6A is based on CPT value, means corrected CPT value, you can calculate the CRR, and the second one is for SPT, corrected SPT value, you can calculate the CRR, and third one is the DMT, like if you have conducted dilatometer test, then from that you can get the KD value. Based on the KD value, you can get CRR ratio, like cyclic resistance ratio. But these three charts are applicable for earthquake of magnitude 7.5 only. So for other than 7.5, you need to multiply this MSF, that is magnitude scaling factor. And if you compare the K sigma, that is the overburden pressure correction factor, the proposed means K sigma in our recent 2025 version is this one, which is function of both effective pressure and also this corrected tip resistance and corrected SPTN value. However, in the previous version, like IS 1893 part 120 2016, here it was only function of effective stress, and this factor F was nothing but it is related to the density of the soil. So for loose case, it was 0.8, and for dense case, it was 0.6. However, here at least we are considering the exact estimation of this tip resistance and SPT value at that particular depth. then it is recommended that if the site is near the area around Koena, you need to consider the maximum value of earthquake to be like 6.5, and for respective other zones, the magnitudes are given here. Table number 6, you can check the code, and then based on this CPT value to find the CRR 7.5. So from SPT, CPT, DMT and our Venn shear test, we can calculate CRR 7.5, and anyway we need to multiply magnitude scaling correction factor and K sigma for getting the capacity, that is the cyclic resistance ratio for a particular zone or particular site specific condition. So CRR 7.5, and this under atmospheric pressure, 1 atmosphere pressure, is calculated by using this expression. If you see, this is a function of E like QC1 NCS. So this CS stands for fine content correction. If you have applied fine content correction, then you need to consider this corrected tip resistance while calculating the CRR 7.5. So this QC1NCS is QC1N plus del QC1N. So this QC1N is only normalized to your overburden pressure correction factor, and this del QC1N is related to your fine content correction factor. If you see here, it is this overburden pressure corrected N well QC1N is considered here. In addition to that, FC means your fine content has need to be considered for calculating this one. Once you have this QC1NCS, you can get the CRR 7.5. So QCN you need to normalize with your 1 atmosphere pressure. So PA is nothing but 100 kPa, 1 atmosphere pressure, and CN is your overburden pressure correction factor, PA by your effective stress, and this M value is also a function of your QC1N and CS. So and this expression is valid for QC1 and CS between 21 to 175. So for other higher than that, you need to means like the soil represents like stiff, so it may not liquefy. So this is only applicable for this range of your corrected tip resistance. And FC, fine content correction factor, you can calculate using the this expression, which is also function of IC and CFC. CFC is minus 0.07. However, IC represents the soil behavior index, means what type of soil it is, whether it is purely clay, silty sand, that. Because in CPT test, we are not getting any sample, means we are not able to conduct the sieve analysis to get the percentage of fine as compared to SPT. So here indirectly by using this IC like soil behavior index, we need to relate what type of soil it is. So this IC is a function of Q and F, where Q is related to your normalized tip resistance, like your QT is your tip cone tip resistance minus total stress, PA is atmosphere pressure, and PA divided by your sigma VC dash means effective stress, and N value is also varies. So for sandy soil it is 0.5, and for clay soil it is 1. Depending on the soil condition, you can take the appropriate N value. And this F is related to your friction ratio, slip friction ratio, which is related to your friction resistance obtained from your CPT test, and tip resistance minus sigma VHC. So once you have calculated F and Q, you can substitute here. You will get the soil behavior index, then substitute here, and you get the FC. Once you have FC, that FC need to be used here to get the del QC1N. And once you have del QC1N, the corrected QC1N CS you can calculate and substitute here to get the CRR 7.5. That is only for magnitude of earthquake 7.5. So in previously, if you check the 2016 version, so there we need to vary this N value to check the type of soil condition. Like N value 2 range is given, 0.5% and 1 for clay. What will happen for other type of soil? So for that we need to means run this loop first we need to assume N to be 1 because CPT test is recommended for clay soil. So let the soil to be clay and then calculate IC based on the F and Q value. If it is greater than 2.6, that means soil is clay. So clay soil is non-liquefable because it will have cohesion term. So non-liquefable means no need to go for further calculation. You can stop there. You can say this particular soil will not fail due to liquefaction. It may fail other due to other reason, but not due to soil liquefaction. So if it is less than 2.6, that means the soil is not clay. Your assumption is wrong. That is n is equal to 1. So you need to change the n value to zero point 0.5. So let us assume n value 0.5, that is for sand. Again recalculate F and Q. Again IC value. Check with the standard light is 2.6. If it is still greater than 2.6, that means soil is not purely sand, it is silt. So you need to change the n value little bit higher than the zero point 0.5 and less than zero point 0.1. This way you need to run the loop and find the appropriate IC value, like particular n, then calculate the CRR 7.5. That in this way, this CPT based method is little bit time taking or time consuming, you can say, because we don't have soil sample with us. So indirectly we need to check what will be the fine content, means for this particular type of soil based on the soil behavior index. But SPT, you have soil disturb sample, you can go for gradation sieve analysis, exact amount of fine content you can calculate. So this second case is for CRR 7.5 calculation from SPT n value. So here also corrected SPT n value after applying fine content correction we need to do use here. So this N160 CS, it represents corrected n value after fine content correction. So n, it which is sum of your n160 plus del n160. N160 represents your Cn n60. So Cn is nothing but your overburden pressure correction factor, and n60, it represents at least 60% of energy should transfer from the hammer level to your required depth. And your SPT test is the n value, it depends on many factors, what, how much energy has been transferred, what type of rod you have used, and the length of the rod, diameter of the borehole, sampler type. So many factors are there. That's why we need to apply this correction factor to get this N160. All these factors has been mentioned in this table number 7. So depending on the your hammer type and this rod length, borehole dia, sampler type, you can get N160. Then multiply your overburden pressure correction factor, which is PA divided by sigma B, and to the power m. M is also function of your corrected n value. Once you have this one, then FC already you are getting from your sieve analysis result. So that's why for FC calculation in SPT based method, there is no additional expressions. Directly you can get how much, means fine content you have, you can use there. And this table 7 can be used for getting the appropriate value of your this CE, CB, CR, and CS. CS is related to S stands for sampler, R stands for rod length, B stands for your borehole diameter. So means normally it is recommended 65 to 115 mm. For that it is 1. If other than that, means you have different borehole dia, appropriate correction factor value you can take. Similarly, depending on the type of hammer, you can use this energy ratio correction factor. Next is third method is based on DMT, CRR 7.5 calculation based on dilatometer test. So from dilatometer test here, this is also a means without borehole you can do this dilatometer test. So here we can get the pressure volume relationship. From that, this horizontal stress index we can get KD and ID material index. So depending on KD and ID value, you can calculate the CRR 7.5, and the value is limited to 1. Other than this, if your KD ID is outside the given range, you can use the figure 6C, which was mentioned in my previous slide here. So this third figure can be used if you have different KD value, like this one means ID less than suppose 1.2 and KD out of this range, then 6.C is recommended. Fourth method is the last method for CRR 7.5 calculation is the shear velocity measurement. If you have shear velocity, because here for doing the shear velocity also you need to perform the advanced testing. That is, you can go for seismic downhole, seismic crosshole tests to get the depth-wise VS information. So highly advanced test, so chance of error is less in zero velocity measurement. That's why the correction factors are less here as compared to the SPT, CPT, and DMT based. So here CRR 7.5 calculation, you can calculate the this VS1 and VS1 star. So VS1, if you see here, VS1 is the overburden stress corrected zero velocity. So only overburden pressure correction factor you need to apply here. PA by sigma V naught dash 0.25 into your measured VS, whatever you are getting from the field, ABR constants. And VS1 star is the limiting upper value of your zero velocity, VS1, for liquefaction occurrence. So depending on the fine content, if you have means fine between 5 to 35%, then you can use this expression. And if it is less than 5%, this VS limiting value is 215. And that you can use here in the CRR 7.5 expression. So second case is for your clay and plastic silt, which is not like liquefiable. There you will get residual strength. So, but cyclic resistance ratio can also be calculated based on CPT, DMT, and empirical relation. If you have this normalized tip resistance and horizontal stress index already you have calculated for your DMT based and CRR calculation and overconsolidation ratio, then this CRR can be obtained. For this is for clay and plastic silt. Once you have CRR and CSR, so if you see CSR is the demand and CRR is the resistance or capacity. So for CSR, we need PGA value and the total effective stress information and the stress reduction coefficient. However, this resistance, we need at least field test result. SPT, CPT, or DMT, or VS. So if this ratio CRR to CSR is less than suppose 1.2, then soil is said to be unsafe and it is prone to liquefaction. And if it is between 1.2 to 1.4, the ground settlement resulting from the earthquake loading, it shall be verified based on the figure 7, which next slide, depending on the RD of the soil layer. RD means relative density of the soil layer. You need to check the settlement value. And if you are getting this ratio more than 1.4, then soil layer is considered to be safe and non-liquefied. So this graph or this figure you need to use for the second case. Like if your factor safety against liquefaction is between 1.2 to 1.4, then depending on the case, means like RD of the soil, relative density, starting from loose to very dense, 90%, 30% is loose case, 90% is very dense case. Seventh one, if you see here, for seven represents the dense soil. So for dense soil, obviously there will be less volumetric strain. Volumetric strain is less deformed settlement, and for loose soil there will be more settlement. So depending on this factor of safety against liquefaction value, you need to check the appropriate this volumetric strain. And the means codal provision means particular structure, what is the limiting settlement value recommended. Actually, till this, it is mentioned in our IS code, for the liquefaction potential evaluation and the settlement. And which for this, we need to have the field test results. But if you don't have that exact field test results, you have only lab-based, like basic soil information, then also you can evaluate the liquefaction, that is the numerical simulation. So there are many liquefaction evaluation tools are available, like open source. They are free to use. Check 2000 University of California, Berkeley, they have developed, and you can use for your ground response analysis. Deep soil is also another means open source tool. Student version is also available. University of Illinois, they have developed, and cyclic 1D is also another open source tool for ground response analysis developed by University of California, San Diego. So these are the means tools that can be used for liquefaction potential evaluation, like liquefaction ground response analysis. You can get this cyclic 1D from this website. If you just write soilquake.net, there you will get the setup files and a link for installing the cyclic 1D, and it is very simple and user friendly also. So particularly this is a nonlinear finite element program for 1D ground response and site specific amplification and liquefaction simulation. And it operates in particular important thing is it operates in time domain. You can consider the exact time history also while analyzing. Parameter required for this cyclic 1D use: you need to have the soil information, height, type of soil, and profile also, like sloping region or level ground, type of soil, water table, bedrock, input motion. And procedure is you need to select the analysis type, that is elastic or plastic. Input values, soil parameter, means whatever the soil parameter you have, density, C value, and friction angle value, that you can give. Profile information, groundwater table, type of bedrock, motion type, damping coefficient. This is typical means model soil profile you can find in cyclic 1D. So ground, I mean, particularly ground response analysis without any structure, you can analyze whether it will liquefy or not numerically. This is the typical input window of cyclic 1D. You need to select the analysis type. Here you can give the model profile, and you can use the user-defined setting. Suppose you need to consider our Indian earthquake. So here you can use USEC, and whatever the input motion data you have, you can select and analyze the profile considering the Indian earthquake. Input most typical, you can see time history acceleration with time record. And response means after analysis you can get the horizontal deformation, horizontal oscillation, excess pore pressure, effective confinement, shear strain, shear stress. So for liquefaction we are more interested to know the how the excess pore pressure is varying. So depending on the means loading condition, soil type, you can get the this pore pressure variation with depth also. So acceleration response you can get excess pore pressure. Here it is so zero because the water table was considered at 2 meter in particular case. So at zero depth, if you see, this is at zero depth, means yeah, at excess pore pressure is zero. And confining pressure, obviously your confining pressure increases with depth, so this you can get. And the shear strain, shear stress, in addition to that you can get time history also, how with the time the your acceleration profile is varying at different location and different time. So once you have this information based on your project type, you need to recommend the mitigation technique. Okay, suppose the site is prone to liquefaction. So before designing the actual structure, let us improve the soil condition or ground condition by applying appropriate mitigation technique. Then go for the actual construction of the particular building. So I means even you have the grain size analysis, your gradation curve. If you superimpose here, this zone represents most liquefiable soils within this range, which is nothing but your sand, gravel, and few portion of the silt. If you see clay, sand, clay, silt, sand, and gravel, so liquefiable zone is mostly within, means it is covering gravel, sand, and only this much portion of your silt. Clay completely non-liquefable. So depending on your gradation curve and whether it is sandy type or clay type, silty clay type, silty sand type, you can use appropriate technique. So for sandy soil, normally grouting, compaction is recommended. If fine particles are there, you can go for like jet grouting, compaction piles, deep soil mixing, soil improvement. That means techniques are recommended. Stone column is also recommended if more fines are there. so that it will provide additional path for pore pressure to dissipate. Vibrocompaction to means densify the soil so that void space can be reduced and effective stress means can increase. Then vertical gravel drain vibrocompaction technique. Grouting can be used, deep soil mixing. There are many techniques are available. So depending on the soil condition and the zone of liquefaction, whether it is at shallow depth and greater depth, and also like you need to decide the cost also, optimize the cost so that with minimum means cost you can get the better result, and mitigation technique that should be recommended for your improvement technique. And once you have means applied the appropriate technique, after the improvement again you need to perform the field test like SPT, CPT or DMT and VS, any one of the test. And after improvement you check the change in the profile, like the resistance value, CRR value. Then you can recalculate the factor of safety against liquefaction. If it is satisfying, means greater than 1.4, then it is, you can say the soil is safe against liquefaction. You can go for actual building construction. So this is, I think, all about your mitigation technique and the procedure to be adopted for evaluating the liquefaction. And